Let's do a review of what I've done since the last video. My computer forced restarted on me, so I lost some of the breakpoints, so I might not go over everything if I forget about it. So anyways, let's refresh and take a look at what we got right now. So you'll notice the pattern looks a little bit more splotchy now. That's because this area right here is encoding a viewport rectangle, right? And there are 4 points to a viewport rectangle. Over here is also encoding a viewport rectangle, and over here as well. I put them in these spots just so I could, I was moving them around to get an idea of, if all of the math was working correctly. So anyways, we're going to move over to here. So the shader sampler now, I have different slots for different shaders. And I have shaders 1 through 9, including, well, 0 through 9, I guess. Yeah. So this is 1. This is 2, just, flashing right now. And then 3. And then 4. And then 5. And then 6. And 7, 8, 9, and 10. So I'm not going to put detailed shader code in each one of those right now. They're just placeholders. If I ever want to test out shader logic, I will put it into one of those unused slots that just has a color, right? So this was from a tutorial I did. I kind of put my own flair to it. It was a tutorial by a guy named Lewis Lepton, and he has some pretty cool, concise GLSL tutorials I did. So anyways, let's get into it. Let's show you what I got here. We're going to scroll through the whole thing and stop at the breakpoints, and like kind of last time, and maybe I'll try to scroll page per page since there's a lot here. Can we do page down? Let's see if I got breakpoint 60 there, what happens if I go page? Oh, no. Oh, because my... Okay, if I'm at here and then I go page down, where is 60? Okay, that's pretty decent. Oh yeah, but you can't see that, so it doesn't matter. Okay, let's just scroll as usual, I guess. So let's see, there's a breakpoint here. Why is there... Oh, that was just me testing. Okay, so, this area, GPU, CPU, sync all variables. I have this section, persist viewport rectangles. And this little stamp here means pixel fog, and the idea is that some data structures in this code base will exist within the actual pixels. They won't actually... The data structure won't actually be instantiated anywhere permanently. It'll only exist within the pixels, just to make sure I don't have two different... I don't want multiple copies of the same data running around to the point where I can't figure out which one is the fresh copy and which one is the dirty copy. So I decided that for these rectangles here that used to be part of the graphics adapter, I completely ripped them out of the graphics adapter, and now these are temporary allocations. So see the let keyword? These are temporarily, so they're they would be C automatic variables. They're stack allocated and have a scope lifetime. And I'm just using these to set up some of the values within our collection of pixels on the master memory that will be storing the canvas rectangle, viewport 0, and viewport 1. So we have the global data.initial values. We'll make that more concise and just call it IV as a temporary prefix to shorten some of these lines of code. And so VPC stands for Viewport Canvas. And these are the initial values we have in our global data. So this is just like initializing those values. Same thing with here, right? We're just initializing all of these rectangles, right? We're loading them up with the correct coordinates from our configuration, and then after we've done that, after we've loaded them up, we're going to use these to actually load these rectangles into our pixel buffer, our specifically the uniform pixels for the master memory, but within a sub-allocation. Right now I have this prefix called lostVar, and that's because I didn't quite know what this variable should belong to, so I made up this prefix. Now I'm pretty sure, as I was refactoring, I'm like, oh, of course it probably belongs in the not adapter variables, but the adapter graphics is what it should conceptually belong to. But then I pulled it out of adapter graphics after I was thinking about how I didn't want my data to get tangled. So this now I'm pretty sure that this should be a global variable. So lostVar is, for me in my code, that means it's a global variable, but I'm not sure it should be global. So it's like an orphan variable. And I'm like, and so I've put it in the global scope because I don't know where else to put it. In other words, if you see lostVar somewhere, that means I don't know what the hell I'm doing, is what that means. And I just had to make a decision of where to put it. Okay, so after we persist the different rectangles into our pixel buffers, right, we're going to leave this scope, and then these rectangles, they're bye-bye, they're gone. And that's because I don't want to have the copies of the data like in two different places at the same time, except for the exception of CPU and GPU, right? Because these rectangles exist simultaneously in GPU data and CPU data that's synchronized. But this, I guess, would be a third copy that's not part of that tightly coupled synchronization. Okay, let's keep on going down. How much time we got? Okay, we're at 7 minutes. This is going to take a while. And so to make the editor kind of be a little bit more user-friendly on startup, in editor 1, I'm putting the selected shader index to 0, rather than it just starting with whatever random pattern was generated into the master memory when we put those test fill patterns. You'll notice that I have this edit 001. This is the constant form of the variable editor 001, like this. And why I wrote it this way, I refactored it from something like this. Like originally it was put eddy 001 dex and like that, but it's very hard to tell what's what here. So this is the variable, and then this is the object it belongs to, which I like because this is the literal object name. However, when we're creating our constants that are associated with this object, this just doesn't read as well as I would like it to. So this is the constant form of this object. So they both mean the same thing, but they're just different visual representations to make things easier for me to visually parse. Going down. Okay, that has not changed. Okay, so I'm going to go down to here. Nothing's changed. I'm going to go down to here. Okay, so viewport. I believe these design notes must be new. So the viewport's VPC always fills the entire canvas, or if a Win32 application fills the entire client area, the OpenGL/WebGL, not BL, viewport always fills 100% of the viewport canvas. Thus, VPC can mean canvas, GL viewport, or client area. This ambiguity is intentional because they should always be identical. So that's a bold design decision. Hopefully it won't come to bite me, because I'm basically saying I'm not going to make a distinction between these different viewport types because they should all be snapped exactly onto each other. So that means I'm never going to have like a OpenGL context that doesn't fill the entire window if it's like a Win32 application, and if it is a WebGL application, I'm never going to have an OpenGL context where the viewport doesn't fill the entire canvas. So that's a design decision that I'm going to stick with, and hopefully it doesn't bite me later, but I don't think it will. I have a pretty clear goal of what I want this to do. Okay, so this right here is the initial viewport canvas width and initial viewport canvas height, and we're going to set that to 512 and 512, which means that it will be the exact same size as the span of the isolated memory. Span being the width and height, because we're assuming that width and height are both identical for these textures or these memory regions, which, because we're using power of 2 textures and we're trying to keep everything nice and square, that will be the case all the time for any memory. Any memory that was allocated on the GPU, it's always going to be completely square and a power of 2. So therefore I use a variable like this sometimes, SAN, and that means width or height, because they are identical. So it's kind of like defining a constraint. Okay, let's go a little bit further down here. So this is those initial viewport sizes. Okay, TU0 texture as uniform. Okay, so it looks like maybe I have, this was an old prefix, because now it's, you know, this. I believe this was before. I'm like, okay, well, if I need more than, you know, 0 through 9, I'm going to be in some trouble. So I'm like, okay, let's change that. Okay, so here's our 8x8 block of texture memory that is partitioned from the master memory for mapping uniform values onto a texture. So this is an inclusive rectangle used to define that region, which we've already kind of been over, but let's keep on going. So what do we have here? Uniform enums. Indexes? Yeah, that's probably the right spelling there. They must be non-negative, within bounds, non-overlapping. So these are just some constraints of how we're mapping the data. And that actually applies to down here. These values, like any of these values you see here in the green, none of these values can be identical, because that would mean you're storing the same data. You're storing 2 different data points in the same pixel, right? And then they're going to memory stomp each other. So that'd be bad news for you. So this is my little visual debugging guide. So right, my memory is a 8x8 chunk. So that's 0 through 7 on the X and 0 through 7 on the Y. And I have the numbers inside each cell are the index location, right? So the last index location will be 63, because it's 0 to 63, because there are 64 unique locations. And that's why you might see like these random non-sequential numbers. That's just because I'm kind of like debugging and trying to make sure that I'm working with the data I think I'm working with. So the viewport canvas rectangle, its data has been encoded in cells 48, 49, 57, and 48, 49, 56, and 57. Viewport 0 is encoded in 54, 55, 62, 63. Viewport 1, 27, 28, 35, and 36. And these are the where these 4 pixels these are the index location of the 4 pixels, index location of 4 pixels, index location of 4 pixels, and index location of 4 pixels. And those 4 pixels are where the data points for x0, x1, y0, and y1 for the respective rectangles are stored. So that's a mouthful, but the idea is that this is just the nitty-gritty details of how I am mapping, I guess you could call them fake uniforms, to a texture subregion on the master memory. This right here is texture as uniform, group number 1, enumeration cap, and the enumeration cap is 64, because capacity means the maximum possible length. So I have a little note here that len is 64 for length, and then maximum index is 63, in case the number 64 is somewhat ambiguous, right? We want to avoid those off by 1 errors. The reason why I used a length value for here is so that if we use up all the way up to 63, this number will be sequential with that, right? The last value for one of our enums could be index slot 63, and then we'll see a 64 here, and everything will be nice and sequential and ordered, and it'll be great. Okay, so let's keep on going. So these comments here were pertaining to some of the stuff up here, but I realized that I really cannot be peppering all of these values with comment lines in between, because if I screw any of this up with the ordering, or especially if I have 2 values that are identical, I'm going to be in a world of hurt. So I need to group these lines as closely together visually so that I can detect if I've made any mistakes. Because if I make mistakes, just weird things are going to happen, and nothing's going to tell me that it's happening. Like, if it happens, just weird stuff will happen, and it'll be up to me to hunt it down. So I want to be very careful with doing this. Now I think if you use a normal uniform and you're specifying the locations, you'll get like a compiler error, or also the locations, like these locations, would be automatically assigned in the shader code. So I'm doing stuff quite manually. Okay. Let's keep going. So like I said, these comments here pertain to the mapped locations on the master memory where I'm storing those uniforms. Scrolling down. Okay, so these are the event bits for the keyboard. We already went over that. This is our hot swapping rectangle, which we haven't really used the hot swapping rectangles yet. It's just a thought for the future when we're actually getting into some more of the actual level rendering. Okay, so this variable isn't very useful anymore, but I decided still to keep in this error, inspect to see if the code has been broken. If this is no longer 512, I feel like that can still be a little bit useful. So this is the viewport canvas width, viewport canvas height, and I just put them into some shorter variables so that I can work with them further down in the code. And so let's go further down in the code. There really should be breakpoints here because I know I did this since the last video. And if we scroll down, we have these values here are no longer hard-coded as 512. Well, actually, that was fixed a long time ago, but now they don't. It's not BOU anymore for bounds. It's these values, and I feel like this might give me some weird things now, because the initial values are being set to negatives, but when I sync with the GPU data, they're unsigned integers. So just some type of negative numbers will end up being very high positive numbers. It's still going to be junk data, but it's not going to be negatives. So I don't know if that's going to come back to bite me. We'll see. Okay. And this is initial rectangle viewport 1 data point x0, and then, you know, same deal with these, right? Viewport canvas, viewport 0, and viewport 1. Okay, let's keep on going until we hit 30 minutes. Okay. Okay. See, configure TAU001. I think we already went over this. Borrow pointer as weak reference. Right, so this is assigning the mapping region to our object that is going to manage the synchronization between our CPU side pixel buffer and our GPU side texture for mapping those uniforms that are stored in the texture. Right, and we're going to use the master memory. We're going to use a subregion of master memory to do that. Let's keep on going. Okay, nothing new. Nothing new. Okay, so some this red here, it means I have removed something, but I wanted to explicitly show what's not here anymore. So the rectangles that I initially had as part of the graphics adapter, we're inside of the adapter graphics right now. And we never actually use these rectangles anywhere in the adapter graphics or anywhere at all, actually. So it's very easy to take them out. I think it's because I was modeling this code after the previous playlists code, which is this file right here, and that's kind of where I think that's probably where I had it before. Actually, no, it looks like I had it in global data. But anyways, I guess it was just a guess at where it should kind of belong, and I was wrong about that because it doesn't belong anywhere, because it actually only exists within the pixel buffer. It doesn't actually exist as an instantiated struct anymore. The data for the struct actually exists, but it's no longer formalized in struct memory anywhere. Okay, so let's go down here. So let's see, viewport rectangles. So I'm just making a note of this was basically moved to initialize a global 002. So the 002 is the second initializer that comes after, in order, global configuration, global data, global functions, global classes, and then global initializer 001, global initializer 002. So any of these numbered initializers are just kind of miscellaneous initializers that are configuring things after all of the objects have been initialized. Basically why this has been moved is because these rectangle instances no longer exist anywhere, and definitely not on adapter graphics. So this has changed in how we did it. I think we already have covered that further up in the file, right? Because we have this IV for the initial values. Yeah. So we definitely covered this the code that is a rework of this further up, so I'm not going to go into any more detail there. Okay, so scrolling down. Okay, our texture containers. Okay, so that hasn't changed. I don't know if I ever went over this diagram or not, but this is just talking about pixel centers in OpenGL and making sure you have the correct formulas that are accounting for that. So I may have changed some of the shader code. Yeah, a lot of the shader code has been changed. More than I put. So okay, there's VP. So there's the. Okay, so that needs to be unhard coded, and I did make a note of it. So instead of using these hard coded values, we have the. We now have those texture pixels that are encoding the bounds of viewport 0, which we can use to calculate the width and height. So we want to not use this anymore and create a function that will grab it for us. So this is the actual bounds of the memory region where all of the data is encoded on the master memory. That is not new. Is this new? Nope, that is not new. Okay, so this, okay, is this new? I see breakpoint. Okay, I refactored the name, but besides that, this is not new either. These two lines here. However, now that we get to here, so this section with the VR, there's quite a lot here. But we have the encoding for the viewport canvas, viewport 0, and viewport 1. So now our shader can get access to these viewport values, which will be helpful because now we can do things like zoom in and out of a shader by controlling these values. We also have to, factor in the usage of these values into the shader code to get that to work, which we're going to do I'm going to do probably next, but I have not done that yet. So what else? Right, so I'm using defines, right, because these locations are not going to change after the program boots up. That would be, like, you could do it if you wanted to. I don't see how it would be helpful or useful in any way. It would just overcomplicate things. Knowing exactly where these bits are on the texture memory is very helpful, right? Because then you can just, go into, right now, shader number 0 in editor number 1 is actually just a view of that texture memory that is encoding the uniforms. And it's nice because I can look at the source code and know where these values are encoded, I can get visual confirmation that they have been set in certain locations. Okay, let's go back here. So, not really going to explain that any more than it has been. Okay, what has changed here? There's, I believe we've already went through mod U32 and I32, right? Just integer versions of modulus. The sampler for the texture as uniform set number 1 using X and Y pixel positions. Sampler for texture as uniform set number 1 using a linear index. Texture as uniform set number 1 U32. What the hell is that? Get encoded value as its original. Okay, yeah, so this one, so this sampler returns a UVec4. And this sampler also returns a UVec4, but we need something else to actually like unpack the value from the texture, or I guess repack. Okay, because yeah, so all of our pixels have 4 channels in them, but those 4 channels are being used to encode a single unsigned integer, 32 bits. So this is repacking those values, right? We did similar bitwise math to unpack a uint and put them into the separate pixel components within the CPU side code. And this is the inverse of that. So we're repacking those components so that we can get the original uint 32 that was on the CPU side. And lucky for us, WebGL, WebGL2 does support bitwise operations. So I didn't have to do any weird hacks. I can just write it with bit shifts. So that's pretty cool. I like that. Let's go. Okay, so Texel fetch, isolated memory. That's nothing new. Texel fetch, isolated memory, rotated. I don't know if I ever covered that or not, but basically we're just rotating the X and Y around the center point of the texture, and then taking a sample. And that the effect of that is getting an animated rotated texture if you sample the entire texture for every pixel. Okay, I gotta stop recording at 31 and then I'll start again.